Alright, so looks like I'm getting my start a little early, so I do have a lot of slides to go through. If you do have questions, I ask that you wait until the end. If they're burning questions and you feel like you'll forget them, then go ahead and shout them out. And I'll answer them as I sort of go through the presentation here. So, high throughput and lightweight web applications for modern use cases. So the overview of today's presentation, working with Caucho. So anybody here, show of hands, have you heard of Caucho technology or used the Resin application server? 1, 2, 3, a couple up front, okay. So we'll just look at who we are, Caucho technology, the Resin Stack. We'll go through some patterns in Java architecture, some of the new trending Java architecture patterns that have seemingly popped up, I guess you could say at the start of 2016 and 2017. They kind of had their do or die moments. Look at some of the faults in the traditional Java architecture that's out there, and look forward at engineering a better underlying architecture. And just the precursor, I won't be talking about protocols, and I also won't be talking about packages. So those will be topics for another talk. So just quickly, who we are, Caucho Technology. We actually started in 1998. I've been with the company myself about 9 years. Back then when Scott Ferguson made the first server implementation, the only competitor was JRun. So Salesforce launched on us as a startup, actually in early 2000. 2012, we got a NetCraft survey that said 4.7 million sites were deployed on the Resin application server. And then most recently, NTT Data, who is our partner from Japan, told us that they've achieved over 5,500 customer sales, all powered running on the Resin application server. So the Resin Stack, just so that you guys have a familiarity with what I'm talking about when I do say Resin, pretty much everything in blue is what we implement and do in-house. So Resin Stack includes a load balancer, a proxy cache, a web server, Resin JMS, which recently has been replaced with message queues, the Resin application server, Resin cache, which is also swappable, so we've had a lot of people using Memcache or any JCache API compliant modules there in the back end, and then the database we don't do. But across the spectrum, we do Resin application monitoring and management. So within the Resin Stack, people are using us to deploy their own cloud. Some users are actually embedding Resin within their application because the Resin package, in total it's about 30 megabytes in file size, but if you strip out some of the Java web profile stuff that we had to implement, you can get it down to about 17 megs. So we're pretty lightweight in that terms. And the Resin Stack, why are people using us? Well, really, like I said, we provide all of the components in-house that we've really seen as vital for scaling a web application architecture. So we were actually the first implementers of the web profile. We still have the fastest server implementation out there, so that's according to TechPower's benchmarks. Once your app does work well in a single server, scaling it within the Resin architecture is trivial because all the components are maintained by us and made in-house, that we've optimized them all to work well with each other. And some of the advanced features that people are using within Resin would be our automatic JSP recompilation. So if you make changes to a JSP page, we can deploy that without having to restart your application, so people can see sort of live updates, live coding, not completely like JRebel, but a lightweight version of JRebel. Health and monitoring and Elasticsearch as well as some of the advanced features that people use within the Resin Stack. Okay, so architecture comment. Beginning, I'd say, early 2000s, we have the Spring MVC model view where we're working with a lot of JSPs, servlets, and a database in the back end. So this was sort of the WSDL, what you see, what you get. Promises in terms of we're going to keep things loosely coupled, but of course heavyweight XML, the spec of EJB itself, and some other underlying components really meant that in terms of achieving loosely coupled architecture and loosely coupled components working underneath the covers, it's not really what we saw. So a lot of tedious and verbose boilerplate code. Using the session object too much in struts was a developer's concern. And state often gets moved from the middle, right? Because when we're talking about the business logic itself within the application doesn't hold state, but it modifies state. So we had this sort of state in the middle with these portions of our application that were supposed to be stateless. But the pro of it, of course, is that it's proven and scalable. So just looking at an image I'm sure you guys have seen many times, how many, by show of hands, have an application architecture out there right now deployed that's similar to a 3-tier stack in production right now? Okay, so I'd say about half, maybe a little bit more than half of the room. Mid-2000s, I'd say, the updated version of this stack comes along, mean.io, using something like React.js, Angular, Node.js, and a backend, more scalable backend database like Cassandra. Really, you're looking at an updated LAMP stack. Sometimes you're using a Datagrid. You might be, have 100 gigs of data, 100 gigs on your hard drive, and 2 terabytes in memory for your storage there, because somehow your architecture is storing more memory than it is in the database. You're using more memory. But essentially, we're building the same thing with a lot better components. So when we looked at the 3-tier scale, we really run into a lot of the same problems that we were having from the beginning. So with the client side, pushing business logic to the processing end on the browsers, not necessarily a bad thing. You do get into the sort of non-statically typed world there. How much of your logic do you want to keep on the front end, and how much do you want to keep maintained within the back end itself? Load balancers, really hardware is not changing much in terms of maybe just adding a few headers, some weird stuff to the back end that you might see there. But on the web server side, what we typically see is users who start to gather analytics. So really here's where we see resources on the back end tied to their application architecture that essentially results in a fault or a break of their application. So recently, actually, I was on site for a company who will remain unnamed, who had a mobile selector as one of their landing pages and simply wanted to gather some statistics off of that, made a PHP script. PHP script was unbounded in the amount of threads that it can make, and it crashed their entire system. When you start dealing with cache, the question that comes up naturally is the cache coherency. So you might have a connection die while a resource is owned by a single thread. You can have this back-end split brain problem. Of course, Zookeeper and some of these other technologies that are out there are in a way made to mitigate the problems that you might have there on the back end. With the app server itself, a lot of people start to use distributed sessions, which if you're using lightweight distributed sessions can be a good thing within the application in terms of if a server goes down, you can recover without there being an interrupt to your end users. But really, we've seen sessions getting into the sizes of gigabytes, 5 gigabytes, 10 gigabytes, and when you're shuffling all of that data around the back end, it's really resource intensive. So we do know, and of course the database is still going to be a bottleneck there, right? Because you have this entity in which your data is stored. It's the master copy, and that's where everything resides in. So if you ever have a thread making a write, doing some sort of blocking I/O on the back end there, the database often is the bottleneck in most applications that we do see when we sort of troubleshoot there. So how does it scale? Well, it's proven. It does scale horizontally and vertically. So horizontally, you're simply adding machines to it. Vertically, you're going to be giving more memory to a machine. And it is proven out there. So as the show of hands depicted earlier, we have about, I'd say, over half of the room still using an architecture like this. But we do have the question of where does the state exist in a stateless session, stateless system? And the answer to that really is everywhere, right? So a weakness of this architecture is that we do have state in the middle tier, contention within who owns the object, the cache coherency issues that I mentioned before. But we do see that the use case for an architecture like this can reach into the 90 percentiles there. Okay, so moving forward here to architectures that have been taught to death, I think we talk about microservices. So just to take a look at them, explicit boundaries, autonomous, so they should be able to recover by themselves, loosely coupled, metadata-driven. And actually what we find is that these principles are from a 2007 SOA principles architecture, right? So a lot of the words that are described today in terms of microservices are the same exact words that were used to describe SOA. It's just that the modules and the tools that we had to work with, given an API, had to call into an outside entity, modify that data, and then persist that data using another thread. Inherently we were going to be introducing integration points where a lot of blocking or contention within the back end can happen there. So when we look at a sort of microservices high-level overview, API gateway you may or may not have, but looking at just really breaking up a REST API and its business logic into its own deployable entity. Usually they own their own database, and then on the back end they're talking quite often. So easy enough how you can visualize a monolith being broken into multiple microservices in terms of the actual implementation. Really all you need to do is build out REST APIs and you can call them into your monolith, and you have already microservice it. But when we look at scale at large, what do we really see? Well, we see these sort of Death Stars, right? We see Hail 450 microservices, Netflix and growing, Twitter is large and growing. And if you have a very large DevOps team and you're paying top dollar for your engineers, then I think you can afford to be a Netflix and a Twitter and maintain these architectures out there. But we have not really seen the huge adaption of everybody moving towards the splitting their monolith into the microservice backend, because with microservices, one of the things that you're going to get is testing becomes a lot harder. A single performance, a remote call that may have been one remote call can be 6 remote calls now. The deployment strategy, you might be introducing different languages into the stack. So while microservices bring a lot in terms of their promise of architecting better applications, the underlying tools that people are using to build them, often what we see are the same as the 2007 SOA tools, which didn't make sense why SOA is able to describe microservices 10 years before microservices comes into the picture, right? So how does it scale? We do get isolated components, and they are non-blocking, but distribution becomes a question, complexity becomes a question. We introduced the idea of eventually consistent into our backends, and it is hard to debug. So rather than looking at a stack trace, you're looking at messages, right? And you're not guaranteed the order of them. If you're using HTTP2, you're looking at binary headers in the messages, right? So debugging becomes a source of contention within your back end there. So we do also end up with a question of, in a system like this, where does state exist in a stateless system, right? And state exists separately in each system. And the use case that we do see from microservices, what we haven't seen, and I'm speaking just from what we see here at Caucho, and I've seen talking to other developers, we haven't seen all of our users moving towards microservices. We have seen some of them starting to ask questions to us about microservices, to which we asked, did you ever follow the SOA principles? So, funny conversation we have there. But, really microservices, as I did say, SOA 2.0, there's a lot of promise there, but the tools that people are building microservices with often are the same tools from before. So the next pattern that we get into, where really we see a lot of the proliferation of the new tools, and a few years ago, some of these tools were very promising, had a lot of steam, a lot of articles being pumped out about them. Vertex, Akka, Spring Boot mainly configuration mechanism, so that doesn't really count. But Netty, Servlet 3.1, just by a show of hands, who's using these sort of, I'd say, hip, modern modules within their backend? Anybody using Netty, Servlet 3.1? Nobody. Reactive Streams, anybody? Arch, Java? No. One in production? Very nice. Okay. And Kafka as well. So just event-driven, very simplified, high-level overview. What we're looking at producer, maybe a Kafka stream or some other listener that you have is producing a set of immutable append-only events to a log. We have an event loop that's going to be handling those events, and then from the event loop, more events are triggered, and you get this nice flow through the back end in terms of non-blocking, high throughput message passing, whereas beforehand you had the request response model that you were working with. At large, we see that this architecture scales quite well in terms of being able to process messages, but again, we hit the question of where does the state reside. So you have shared state within like an Akka system, you have locks and conditions that you're doing, and you have dependencies within separate actors that might be waiting for a result, waiting for a message, and couple that with the network, with your typical network problems, and we can see why only one person is using an architecture like this in production right now. So, how does it scale? Well, it does scale, right? We see that Netflix and Twitter and Amazon, they can do it. Surely, why can't the rest of us? But it's pretty complex, right? So, you're dealing with a different programming model than Caucho. Getting down to message passing means that in your business logic of your actors, you're really starting to get a lot really fine-grained into what you're building. The Java code starts to take some time, some iterations to go through and go over before you're really understanding everything that's going on there. Okay. And we still have the question, in fact, of where does the state exist? So again, shared state, conditions, locks, states sort of existing everywhere. Within that, you might be parsing data out to another stream somewhere between. So there was an interesting survey on Java Lobby earlier this year. Simply asked people to name the frameworks and tools they're using to build microservices, right? And so what we did see is it was about mid-2017. The survey came out, so Akka was only at 6.6%. I was surprised. Java EE and Spring Boot, really running away with it. And I guess there's really no surprise there. Spring's pulling in a lot of different libraries, some Java EE-like libraries. So what people are using is proven solutions that are out there, yet they're applying now, I guess, more strict in practice, the sort of Martin Fowler type of microservices that have been described. Was there a question?
Why didn't it act to 100%?
I'm not sure. You gotta ask Java Lobby. Might have just been their chart pulls down there. Nobody goes beyond the 50% in terms of the use cases there. So if you add them all up, they should reach about 100. So when we're looking at the faults of previous models, in the servlet model, one of the problems is it's multi-threaded, and while multi-threaded sounds great to begin with, the problem is blocking and locking threads, right? Show of hands, anybody who's had an application crash recently, I'd say the last 2 months because of block threads? Anybody here? I want to see a couple honest people. I know that's more. The database bottleneck. So we only have the end master copy there. So your database is still going to be is within the operational path of every service that you're doing. And looking at some of Vertex and Akka and some of these other frameworks that sort of came out there, they get a bit complex when it gets down to the actual Java code and what you're trying to accomplish, right? Writing a simple chat application may be straightforward, but writing an entire full-fledged bookstore, this sort of auction applications, gets to get a little difficult when all of those messages passing through the actor system need to be asynchronous. You can't ever block, but you do need to be managing state within your logic there. So we take a step back and we say, what are we really trying to accomplish here is how can we scale? So if I take a look at this graph here and they compare systems A and B, showing how well they scale as we add cores. and I would ask, which is the better system? So show of hands, people who think system A is the better system. Okay. Show of hands, people who think system B. And undecided. Okay, a couple undecideds out there. So it's a bit of a quick trick question, because really the better choice of the answer is C, undecided yet, because there's some information I'm withholding, and that's the actual performance. So while we're seeing that speed up of an actual system can be speed up achieved by adding cores to that system, what we're not seeing actually is the performance of that system, also achieving that same level of performance gains. So what we see is system B, what I didn't tell you, outperforms system A at every level of the core, right? And so where this comes from, and these images are actually borrowed from, is a great paper by Frank McSherry, and I recommend it. It's called Scalability, but at what cost? And what they find is that, a couple of key points here. Contrary to the common wisdom that effective scaling is evidence of solid system buildings, any system really out there can scale. What cost does is cost is the configuration that outperforms a single thread. And so what cost does is it weighs the system's scalability against the overheads introduced by the system. And that indicates the actual performance gains of the system. So what Frank and his team actually find here often is that many of the published systems out there have unbounded costs. That is, systems of hundreds of cores all working together, costing hundreds of thousands of dollars, are never able to actually outperform a single-thread implementation of that same application. So there's orders of magnitude slower, even using hundreds of cores. So it's a short read of a paper. Link is provided here in the bottom. So if you do feel like reading that, I recommend it. Moving forward, we'll talk a little bit about Amdahl's law. So Amdahl's law basically says, taking you back to your first computer science classes, that we're always going to be as slow as the sequential portion of our application. So an application can be split into two portions, one part that cannot be parallelized, and the second portion which can. So that's what you're seeing here in the pictures itself. So B is the portion that cannot be parallelized. As we're seeing in the second picture, because the 1 minus B, the portion that can be parallelized, is run at the same time on multiple cores, we see a factor of 2. The third picture, we're seeing a factor of 3 increase, but we still have that chunk, that sequential portion that is always going to be the limiting factor in our architecture. So what do we really want? Well, what we really want is a way to run fast, right? So in memory, we want to be asynchronous. We want to remove the database bottleneck from the back end. We want to eliminate thread blocking because we know that's a point of contention. And we also want services to own their own data, right? So we want services to own and operate their own data because that eliminates the probability that you might have the two versions of an object owned by the resources calling into it, cache coherency sort of views. So when we start to talk about what we want and how we're going to operate, what we at Caucho came up with is we call operational service views within the platform Verity. So just as a reminder, today's applications, and this is taken from the Reactive Manifesto, it's not old solo 2007, so this is updated. We want reactive, message-driven, loosely coupled, and polyglot, and as I showed before with some of the dev stars, it's being done by Google, Netflix, Amazon, Twitter, and anybody else who has a diesel maybe. So let's look at some of the key concepts of Verity. So strong encapsulation boundaries. Each service is going to have its own thread in an efficient lock-free inbox, and inside a service, application code can be single-threaded. So depicting that is what we have here. So there's a proxy. The proxy calls into a lock-free inbox. The messages are queued within the inbox. Within that inbox is what we have what we call the encapsulation boundary, where only a single thread operates within that encapsulation boundary. And what this allows us to do is to get better CPU affinity and spin through these messages in the reactive sort of workday solution as fast as possible. So the threads that are calling in do get callbacks. The service thread spins through, can operate on all of that data in memory, put the results into the outbox, and the outbox goes to the other threads there. So 3 more key concepts. Persistent services load and store to a document-style key-value database. So Veritine does have its own append-only database. Services use their data in memory, so loading and storing is transparent to the user. And services own their own data, so no additional locks are needed to protect it against other services modifying their data. So it means that inside of a service, you're not going to use a concurrent hash map, you're just going to use a hash map. You're not going to make synchronized methods, you're just going to make the method, because within a service, only a single thread is ever going to be operating within that, so there's no point of contention with outside threads touching that data. Just a quick look at the database persistence. So in-memory persistent services are built into Veritine, so the async high-performance internal database is called Kraken. An application service will operate on this data in memory, which improves performance and simplifies code. And then we have that the data is automatically loaded and saved as part of the asset's lifecycle itself. So the use case number 1 that we look at would be maybe for an API engine, right? So you have some sort of clients on one end, and they're calling into an API, which would run as a Veritine service, and what you're getting is within that Veritine environment, single-threaded code, no blocking, no locking, and data is going to be transparently stored and loaded to the user. So, got a little typo at the top, but sorry, there's some odd animations. So at the top, what we see is the traditional bookstore REST service. So threads come in, there's not always a proxy, but the 2 threads that don't get the object first get blocked. The first object goes in, makes the call, makes its write to the database. Once it's returned, the other thread, second thread can then start operating, does the same thing, makes the update, comes back. So operations must be persisted to an outside database. You must use the synchronized keyword around these services, and there's really no thread ownership of the data. That's really far from the course where Veritine is designed, because Veritine is designed at the thread and data locality level up, right? So what we get instead within a Veritine service is the operations are done in memory. There's no locking or blocking that must be done, and we have single ownership of the data. And in a side-by-side comparison, what we saw with the REST easy implementation of JAX-RS and the bookstore REST services, we get over 2 times the performance with Veritine. We can also scale Veritine to match the cores on a CPU, and we can have persistence added with a single annotation. So rather than just continue to show you slides of this, I do have here. Bookstore, so we can run the application here and show you what it looks like. Okay, and I'm not a UI designer, so 456, author will be Sean, title will be How to Give Great Talks. Great Talks. Okay, and I'll author the title, 4567, a second one. And we can look at the current list and we can see that what's going on here is the service is running on the back end. On the front end, it's returning JSON over WebSocket wires to the browser. So we're just printing that out to the console. One thing though would be what happens when the application dies. So I'll kill the application and then restart the application. And we'll see that, oh, still no. We'll see that the database is actually not there. So if we look at the current list, the data was not persisted. The one that you're seeing there is it's in the code itself. Let's bring up the code to take a look at it. We're creating actually just one book within the code. Let's see this. Lost my text wranglers. Okay, here's the text wrangler screen. So it's a simple code drill, right? So there's no magic. It's no message passing. It's simply saying, as you guys can read, we have API here books. We have the get books returning just a simple book itself, and we have an add book method as well. And to run this, we're doing an include bookstore class, name report, we're doing start. So one sort of odd thing that you do get when you're working with asynchronous is the result.ok null that you're seeing here. And that's simply because all of these are asynchronous methods. We have to get some sort of notification that the method has completed. So that's what Veritine includes, the result.ok. But if we wanted to go ahead and add the persistence to this, a couple of annotations is all we're going to need. So let me just clear. The database, make sure there's nothing there. Okay, and we'll rebuild that and run it. Okay, so the app's back up, nothing here. ID will say 456, author could be Frank, and NYJavaSIG. We will offer this title, see it in the list, okay? So now we can go back to the application, we can stop the application, go back to our browser here, make sure that it's dead, okay? We'll go ahead and clear the database, so there's nothing there. I shouldn't have cleared the database. Actually, didn't mean to clear the database. What I meant to show you was that if you don't clear the database, that it is persisted simply by the addition of that, annotation here. So let's try this one more time. Okay, kill the application. It's dead. Restart the application. And when we look at the list,
wrong button, wrong, yeah.
Yes, there we go. When we look at the list, we see that, thank you, that the book that we authored is there, right? So as with other NoSQL databases, we're getting no sort of database schema needed to persist this, and we get the code, we get all of our assets persisted to Veritin's internal database. So let me just pick this back up here. And again, as I said, with the performance of what we saw Veritin versus the typical REST easy performance scales out there, we saw over 2.5 times the performance gains. So this is the entire service itself. So there's no database code, there's no synchronization, there's no concurrency, there's no concerns about thread starvation, performance, and scalability. And as we saw, with annotations, we can simply add persistence to an application. So looking at other performance metrics, when we're talking about in-memory operations, and this was a database on the same network, Veritin versus the traditional servlet model, which is very popular out there, it's getting a lot better performance. So this is mainly because Veritin does not have to go to disk every time. It's doing the operations in memory and it's persisting those afterwards. There's no concerns about it because we're operating within that strong encapsulated boundary of a single thread. So our in-memory operations, just to touch back on this again, so the data is loaded only once, so it's removed on the LRU. All of this is transparent to the user, right? Large data sets tend to will shard well, they shard themselves. So you don't have to worry about one index being on a node that you're traversing that's been replicated to another node in the stack that has some sort of network communication problem. Right through in place, so Veritin saves the fields of the asset to our fully reactive document database and the journaling. So the inbox serves dual purpose. One, it queues the messages, so you get an ordered first in, first out of ordering of the messages coming in. And the second purpose is that we can replay the journal for reliability and failover. So the inbox is backed up and replayed if in fact the server ever does go down, because that tends to happen. So Veritin performance, as we sort of looked at that other system when in the Frank McSherry paper, messages calls per second on a single client are extremely high. As you increase the number of clients to the system, we do tend to reach about a linear scalability. Really what we were doing with this benchmark is we're hitting probably the processing power of our system itself. So under light load, asynchronous performance is about 9 million methods, 9 million messages for calls a second, while the future performance is about 4 million. And as the load increases, of course, the future performance drops to about 0.5, and the async performance drops, but it does not go below 2 million. So use case number 2 that we would look at is the auction microservice. So before, when we looked at that Java Lobby survey, the question was, what frameworks, or tools, or modules are you using to build your microservices? Well, when you're using the same libraries and the same tools as before, underneath the covers you're still working with a lot of that multi-threaded locking and blocking database as a bottleneck aspect that you were using back in 2007. You just weren't calling it that. So when we look at what an auction microservice might look like in Veritin, what we're able to see is we do get closer to the end goals of SOA, closer to the end goals of reactive, loosely coupled systems. So each service would own its own data, multiple services talking to each other, so you're going to run into potential network pitfalls if you do disperse over a large geographic area. But really, we're able to now scale services independently of each other. And if a service does go down, you have a very clean way of abstracting those errors out and not having your entire system crash. So beforehand, when company not to be named had wanted to introduce a metric gathering portion to their front end of their mobile selector, and they chose PHP, and they had an unbounded thread process, continually make threads and block on the front end, which crashed their entire cluster. A Berating service is really isolated to its own environment. So if you put it inside of a Docker container, or a Rocket, I suppose, or another virtualized environment, you've isolated that even further. But what you're never going to see is the threads contention that you might have with the other frameworks out there. And just to give this one a quick run here, because my coworker actually did build a running version. So just some verbose printouts. I'll bring up our local host here. So what we're seeing here would be a sort of a full page single app, so something maybe similar to eBay, but this is, again, it's just a proof of concept. So make a name here, password, 1, 2, 3, create, and I'll log in. We can create an auction with some cars, bids that start at 100. In auctions, what we're seeing now is that's been persistent to the database. I can search it. We're actually using Berating Rapidly Seen to do the search, and we can place bids on that, so you can see the bids do sort of go up. I can make another auction, start the bid at 200 trucks. I'll search trucks. And what you should see there, the reason why this bid sort of goes out is the state goes from settled to open. So we have a timer, just a timer service on the back end that we're utilizing as well within this proof of concept, just because we want to fully fledge it out and hash it out. So part of the difficulties, though, in building this application is the logic dealing with asynchronous portions of your app, because even though it may look like and appear that a lot of the app is running asynchronously in terms of no-block threads, there is some contention to process an application. So this is stuff that you'll see in the normal microservice sort of talks where they look at some of the pitfalls of microservices themselves, right? What we have here is that the bidding service is not the service that owns the data and owns the state of whether it's settled or not. So in the back end, if you look at the code of this, we're doing a fork join. So there are going to be portions within your application that still are going to be synchronous because the business logic demands for it. But what we're not seeing is the portions of the API opened up to the client, and the portions that are opened up to the data are no longer being accessed by multiple threads here. So just getting back to the presentation, again, what we wanted to do was, when we started building Berating, it really started as an in-memory queue, and we were looking to solve the problem of the bottlenecked database and the contention of threads that we were seeing. And so Berating, we brought it to a 1.0, and we've open sourced it, and it is our experimental technology out there that we put out, because we do embrace cutting edge technology, and a lot of our engineering is led by Scott Ferguson. So he's the chief architect at Caucho, and he's been around for a very long time. He was on the original serverless spec expert team. And so really this is a brainchild of Scott Ferguson's, and after so many years of dealing with databases of bottlenecks and multi-threaded contentions, bringing down so many people's applications, really this is the end result, what you see with Berating itself. So as I mentioned, Berating has reached a 1.0 state. We've open sourced it. It's experimental, but It's what we look forward to seeing when we talk about new architectures being developed and actually implementing new engineering principles underneath the covers. So rather than rebranding SOA, these sort of frameworks where the potential to run an entire application without blocking the system, to have great performance on a single thread, very Caucho-like code that you should be writing, are the type of frameworks that we hope to see sort of moving forward here as we continue using Java in the future. So if there are any questions.
So when you initially showed us the resin system, it had all these components. And what is Barentine?
So Barentine is a separate module. It's within the Caucho platform, but it's not within the Resin Stack itself, because Resin is based around the Servlet 3.0 spec, multi-threaded. So Barentine, you can think of it as a library. Okay. So you could use Barentine with Resin, issue with accessing the session object itself, but really what your Barentine is, just consider it as a library that you would drop into your stack and use for the sort of asynchronous portions of your application.
Okay. And how does the overall Resin ecosystem, how does that compare with something like Spring Cloud, which seems to have similar elements that...
Right, so Resin you can actually use within Spring's ecosystem as the servlet container. So Resin fits within Spring for some portions, but it goes back to our principle of what we've designed. So before there was Spring Cloud and Spring Boot, there was Spring MVC, and we were working on Resin. Resin is the libraries and packages that we saw fit needed to scale an enterprise application. So you can use Resin standalone by itself, or you could embed it within something like Spring to use some of those other libraries and pull those libraries in as well. Class path issues are resolved with a sort of just a tag, so in terms of library loading. But Resin runs completely separate. You can run an entire cloud based on Resin. Some of our customers do that. Actually, NTT runs an entire cloud based on the Resin servers. So the two are separate. Sort of started out tackling some of the similar issues and concerns that were in the Java EE world, right? In terms of having to write a lot of boilerplate code and Java EE being loaded. Resin itself, as I mentioned, the package size is about 30 megabytes, but that's because we were required as a licensee of Sun to implement the web profile, and that pushed the package size up from about 17 to 30 megs. So if you strip Resin down bare bones, it's about 17 megs and still run standalone fine. The other portions within Resin are portions of the web profile that we have implemented.
You're trying to eliminate communication between threads, just executing everything in single threads which do not communicate with each other. So they don't work.
Yes.
Did you compare or consider your approach against non-working algorithms? And technically they communicate, but they don't actually work. They can perceive if work is busy.
So are you referring to like Java futures or?
For example, non-working based on those pointing variables, something like this. Non-working algorithm, but threads communicate, but they actually do not wait.
Right.
Threads can proceed to do something if work is busy.
Yes, so within Resin, I mean, that's the way we've tackled asynchronous from the start, is usually using thread pools. So you have a bunch of thread pools, or you have a couple of thread pools with a couple of threads in them, and instead of using a per thread per process or per thread per request sort of model, you're utilizing a thread pool to get some form of asynchronous operations within the application itself. Problem was being always which thread is then responsible for touching and persisting the data. So if you recall, there's two things we were sort of looking to mitigate, not just the contention of blocking threads, but the idea of where data should reside, and that data should, it's our view that a better system would be one where data does not exists in an outside entity, and that the thread that's responsible for touching the business logic is also responsible for updating and persisting the data, because that way, rather than just asynchronous in terms of non-blocking threads, you're getting asynchronous operations where your operations are happening in memory and persisted, rather than your system is flowing, but at some point, some level, you're blocking when you go to touch the data.
So, can multiple threads put in events in the inbox for one of these services? And if so, then how do you kind of keep them from stomping on each other? What's the mechanism you're using?
Multiple threads, yes, can. An inbox, there's only one inbox that's answered by a single thread, but yes, multiple threads could call to that inbox. They would receive their callbacks, and it's that single thread's responsibility to then answer those original callbacks that it did receive. So that's really the technique that we're using for that. One thing I didn't mention is one of the annotations that we do have with the methods is one called workers, where, say you're integrating a legacy system, MySQL backend, where there's going to be a lot of locking and blocking. You want an easy way to speed up a current API. Well, you could use the workers annotation, which says, you dedicate 4 threads to, makes a thread pool on the API, which can then, integrates well with these sort of blocking backends that are in existence today. Because, as I mentioned, we worked on Veritine for quite some time. There's a lot of iterations, a lot of questions and design practices we were going over before arriving at this. But still to this day, Resin's our bread and butter, and so we had to look at a way to integrate, the new age stuff with what people are currently using and doing. So that's where we came up with that sort of principle in integrations.
Have some confusion on your you have a notifier to deal with the async completion of the operation. But if you're running a single threaded process, why not just block and get the result instead of getting notified?
Well, the notifier is for if you're going to do synchronous methods versus asynchronous methods. So we have the notifier in there, the result.ok, that says that this thread can continue its process and it's done doing its work in terms of its asynchronous. Because there's no way, without the notifier, there's no way to sort of have synchronous methods or asynchronous methods consistently receive their callbacks if you're batching an entire queue. So what we're doing on the inbox is that entire queue gets automatically batched over, and the single thread then spins through the results there. So because of the batching technicalities that we were running into, and the fact that Veritine supports synchronous and asynchronous, we needed a clean way, clean abstraction, clean Caucho level programming method to take care of that. Okay, well, if there are no other questions, thank you very much. I'll be available if anybody wants to talk. My email is here, and our website is here at Caucho.com.
Thank you.